We want to prove this orthogonality relation here for matrix elements of unitary irreps. The gamma j's are irreps, and we look at these matrix elements here, and we sum over all group elements, and we get lots of Kronecker deltas. Okay, how do we go about this? We start by giving the carrier spaces names. So let's say the carrier space of gamma j we call Vj. And now we consider some linear map from, let's say, Vj to Vk. Linear and otherwise arbitrary for the moment. And let's build from this A, we build some A tilde where we use the representations of all the group elements. So we take a sum of all group elements normalized by the order of the group. And now we start with gamma k of G, our linear map A, and gamma j of G inverse. So we can do this. The gamma j goes from Vj to Vj, and then the A goes from Vj to Vk, and then the gamma k goes from Vk to Vk. So what happens when we multiply this with, let's say, one of the representation matrices? So let's look at this. Pick any h in G, take gamma k of h and multiply with A tilde. We will see that we can somehow commute this through at the cost of changing from k to j. So let's just write it out. We have 1 over the order of the group, sum over all group elements, gamma k of h, gamma k of g, A, gamma j of g inverse. Now gamma k is a representation, so here we have gamma k of h g. And now instead of summing over all g, we can also sum over all hg. So let's give hg a new name and call that g prime. And then the g here is just h inverse g prime. So instead of summing over g, we sum over g prime. That's applying the rearrangement lemma again. So sum over all g prime in the group, and now we have gamma k of g prime, h, gamma j of h inverse g prime. So what is this? Gamma j of h inverse g prime, that's just gamma j of h inverse. And I forgot an inverse here. Look, this inverse here I forgot. So let's put an inverse out here. Now we have gamma j of h inverse, gamma j of g prime, since the whole thing is a representation, and then an inverse on the outside. So this is just gamma j of g prime inverse, and now we have gamma j of h inverse inverse, but since it's a representation, the last term here is just a gamma j of h, and that's essentially what we wanted to have, because now this whole thing here reads sum over all group elements normalized by the order of the group, gamma k of g prime, A, gamma j of g prime inverse, and gamma j of h. So the first part is just the a tilde, and the last thing is the gamma j of h, which we got through here. So we have a tilde again times gamma j of h. If we compare, maybe we can show this completely, not just. We got the gamma k of h to the other side by changing it to a gamma j of h. And that's exactly the condition that shows up in Schur 2. So with Schur 2 we can now conclude that this a tilde has a very special form. So Schur 2 tells us the a tilde is either 0, that's if j is different from k, if we have different irreps here, and it's a multiple of the identity if j is equal to k. And we can also calculate this number c here by taking the trace of this equation here. So the trace of a tilde is just the dimension of the irrep times the c. And as we can say, the c is just 1 over dj, the dimension of gamma j, times the trace of a tilde. And the trace of a tilde, that's just the trace of a. Because if we look up here how we defined the a tilde, that was the orange equation here, we conjugated a with these gammas here. And now the k is equal to the j, so we really conjugate it with the same matrix. And under the trace we permute cyclically, and then the gammas go away, and we have as many terms as the group has elements and normalized correctly. So we really just get the trace of a back here. Let's write it out. 1 over dj times the trace of a. And so far this was for any linear map A. Maybe we can write down the a tilde again. Let's do this. The a tilde now is this 1 over dj trace of a, let's say delta jk, that takes into account this distinction here, and then a unit matrix. So this is our a tilde, and so far the a was completely arbitrary, but now let's choose a special a. So let's choose an a, if we write this as a matrix, which has just a single 1 in one place and zeros everywhere else. So how do we write this out in components? Our a, let's say a alpha beta, the components are delta alpha nu prime delta beta nu. And that means that the trace of a, well, it's 0 unless nu prime is equal to nu, unless we put this 1 on the diagonal, and then it's 1. Yeah, so it's just a delta nu prime. Okay. Now we calculate a tilde, let's say elements, maybe I want it like this, mu prime mu. Then we have, using this pink equation up here, we have that this is equal to 1 over dj, the dimension of the representation. Now a delta nu prime, it comes from here, from the trace of a delta jk, which we already had, and then we look at a matrix element of the unit matrix, and that's a third delta. That's just a delta mu prime. Okay, so we calculated this once using the pink equation here. Now we calculate this matrix element again using the definition of A tilde. So A tilde up here, the orange equation, where we have the A conjugated with the representation matrices, conjugated because now it's only non-zero if J is equal to K. Okay, what do we get then? Sorry for switching screens. So what's this? It's 1 over the order of the group, sum over all group elements. And now we spell this out in components. So the matrix multiplications, this is sum over alpha and beta. And we have gamma k of G, matrix element mu prime alpha, A alpha beta, gamma J of G, inverse matrix element beta mu. Okay, but we just calculated, we just fixed the A alpha beta to these Kronecker deltas. So these two sums here collapse to just one term. Maybe I should indicate that now we use the orange definition of the A tilde, and now we use the deltas in order to write it like this. It's only a sum over the group elements again. Now we get gamma k of G mu prime, and the alpha is fixed to nu prime. That's what we see up here. And then we have gamma j of G inverse, and the beta is fixed to nu, so we have mu here. That's what this Kronecker delta here does. And finally, let's use that our irrep is a unitary irrep. So instead of gamma j of G inverse, we can write gamma j of G Hermitian conjugate, and we take the new mu element of that. And what's that? Hermitian conjugation means we have to complex conjugate, and then the transposition means we just have to flip the indices here. So we have gamma G of J mu complex conjugate, and that's exactly the expression we wanted to have in our theorem.